Good afternoon, all and all. I am Bhakti Pandey from Department of Pharmacy, and IIMT College of Pharmacy. So I'll be presenting my topic in video lecture, which is solubility of drugs. So I'll be starting with the definitions. So we have several definitions in this slide. We'll be starting with the solution. So basically, what is solution? Solutions is the mixture of two components, basically two or more components that forms a homogeneous solution or homogeneous mixture. The components may be referred to as, we can say, solute and solvents, or we can say solutes and solvents. So what is the solute? So solute is the agents, or it is the agent that is less abundant in the solvent part, and the solvent is the component which is used to dissolve that particular solute. So the more abundant part is solvent, and the less abundant part is solute. Then comes what is a saturated solution. So saturated solution is one in which the equilibrium is established between the dissolved and undissolved solute at a definite temperature. Or we can say a solution which contains the maximum amount of solute at a definite temperature. Then comes unsaturated solution. Then we can say what is unsaturation, or what is subsaturation. So particularly the subsaturation is that which contains the solute concentration below that is necessary to complete the point of saturation. This is called as the unsaturated solution. Then comes supersaturated solution, or we can say supersaturation. Then supersaturation is what? It contains more of that dissolved particles or dissolved solute that it would normally be dissolved in that saturated ones at a definite or at a particular temperature. So with all these definitions, we got to know about the different terms related to solubility. Now I will be starting with the definition of solubility. So what is the solubility in quantitative terms, and in qualitative terms, and in terms of thermodynamics? So I'll be starting with the qualitative way of solubility. In qualitative terms, the solubility will be referred as the maximum concentration of solute in a saturated solution at a certain temperature. Then comes, in a qualitative terms, we can say it is the spontaneous interaction of two or more substances. Which are the two substances? Are the solutes and solvent. Then what they form? They form a homogeneous molecular dispersion system, or we can say molecular dispersion. Then there are two types, qualitative and quantitative. Then comes the thermodynamic solubility of drugs. So what is the thermodynamic solubility of drugs? The thermodynamic solubility of drug in a solvent is the maximum amount of the most stable crystalline form that is present in the solution, that gives at a particular temperature and pressure at equilibrium conditions, like fixed temperature and pressure. Then the equilibrium involves the balance of energy of three interactions. Basically there are the involvement of three interactions against each other, which are solute solute interaction, solute solvent interaction, and solvent solvent interaction. So particularly we are having solute in the solution, we are having solute and solvent, and we will be having interaction of three types, which is of solute interaction, solute solute interaction, solute solvent interaction, and solvent solvent interaction. Solvent molecules will be having a cohesive forces in between solvent molecules, and they will be having a adhesive forces in between solute and solvent molecules. Then with similar effect, we can say solute molecules will also have the maximum force of attraction with each other, or we can say cohesive forces will act there to maintain the stability of that solute. Then we'll continue with next slide, which is solute solvent interaction. So what is the solute solvent interaction? How solute and solvent will be interacted with each other? So there will be, first of all, there will be a removal of a solute molecule. So in this slide we are having that drug crystal, and in this drug crystal, or we can say a solute drug crystal, a solid particle or a solid drug molecule will be released in first part, that is removal of a solute molecules. Then in solvent molecules there will be a generation of cavity. In this cavity, third part is that insertion of the solute which was removed earlier from that of the drug crystal. Then it will be inserted, or insertion of that solute molecule in that of the solvent molecule. So this is the solute solvent interaction. So by this we can say the interaction of solute and solvent. Then comes same the mechanism of solubilization process from organic solute in water involves the following steps. These steps are same as I have explained before. The first of all, the breakup of solute intermolecular bonds. So first of all, there will be a breakup of that solute molecules, solute bonds. We can say that van der Waals forces or whatever ionic bonds, they will be breakdown. Then after breaking down, then the molecules of solvent will also break down in then they will generate some cavity, or generate some gap for that of the solute molecules. For then after that gap generation or that cavity generation, cavity then the cavity was filled or accommodated by that of the our solute molecule. Then transfer of solute into the cavity of solvent phase and formation of solute solvent intermolecular bonds. Then when after that insertion of the solute molecules, the solvent and solute will form a intermolecular bond which will finally give us a bond between solute and solvent, or we can say perfect interaction between them. Then comes the expression of solubility or solubility expression. We can express solubility in many ways, in many terms. We can say some terms are molarity, normality. So first comes molarity. So molarity is what? Molarity is moles of a solute in 1 liter, or we can say 1000 ml of solvent. Then molality is moles of solute in 1000 gram of solvent. Then normality is gram equivalent weights of solute in 1 liter of solvent. So in other terms, we can say when the solubility is not known for that particular solute, we can take it as is like descriptive terms. Some descriptive terms are there. We can say that what part or which part of the solute can be dissolved in how much part. One part of solute can be dissolved in how much amount of, or how much part of solvent, or how much part of solvent is required to dissolve one part of the solute. That is, first of all, in descriptive term, there will be a very soluble part which is less than 1. It means less than 1 part of solvent is required to dissolve 1 part of the drug. Then comes freely soluble. This is from 1 to 10. So it means what? 1 to 10 part of solvent is required to dissolve 1 part of drug. Then comes soluble. In soluble criteria, from 10 to 30 parts of the solvent. Then in sparingly soluble, from 30 to 100. Then slightly soluble is from 100 to 1000, and then very slightly soluble from 1000 to 10,000, and Last one is practically insoluble, which is practically insoluble. We can say this is cannot be soluble in 10,000 parts or over that. So these are the descriptive terms or expressions for the solubility. Then comes BCS classification system. So we have a classification system which is called as biopharmaceutical classification system. BCS is a scientific framework to classify or for classifying drug substances according to their aqueous solubility and intestinal permeability. So we are having four classes for the solubility or permeability of drugs. So we can differentiate amongst the soluble and means highly soluble or low soluble or highly permeable or non-permeable or low permeable drugs. So first of all, there are four categories. First category is of highly soluble and highly permeable drugs. Means what? Means these are uh, these drugs can give the 100% bioavailability or near to 100 or uh, greater bioavailability as compared to other, we can say. So these are having high solubility and high permeability. This is of first class. Then comes second class or class second, which is of low solubility and high permeability. Then comes third class, which is of high solubility and low permeability. Then fourth class is low solubility and low permeability. So we are having four classes, which gives us the idea about the drugs which that uh, which can be soluble fast and which cannot be soluble fast, or which can be permeable easily or which cannot be permeable. First of all, highly soluble and highly permeable means both criteria for solubility and for absorption is cleared. Then comes second one. Second one is solubility is low and permeability is high. So first criteria is what? First criteria, drugs we need to formulate a dosage form. Then dosage forms in the in the our means in systemic circulation or our GIT. We need drugs in a solution form. When it goes to our intestine or our gastric environment, we can say we need that our drugs should come in a solution form, or when drugs will come in a solution form, they will be better absorbed as compared to solid form. We as we know that it will acquire more surface area, so better will be the absorption of drug. Then comes third class, which is of high solubility and low permeability. So we, as we know that solubility and permeability both are equally important for the bioavailability, we can say, or we can say therapeutical response that we are achieving from that drug which we are intended to use. So solubility as well as permeability is equally important. So third class is drug is soluble but is not permeable. It means ultimately bioavailability will be hindered. Then comes fourth class, which is of low solubility and low permeability. It means solubility and permeability both are low in this case. So these kind of drugs we can't use in our formulation purposes, because or if we try to use these kinds of drugs, we need to work more in in that case. We need to work more for this. Means we have to take solubility enhancement techniques, or as well as we have to take other measures for permeability enhancement. So we generally don't use such kind of drug which have solubility as well as permeability problems. Then comes solvation. So what is solvation? Solvation is the process of surrounding of solute particles with that of the solvent particles to form a solution. What is solvation? In this process, then in solvation process, solute particles are surrounded with that of the solvent molecules. Then it comes under a solution. They form a solution together. When the solvation occurs with water, it is called as hydration. Then there are some factors which can affect the solvation of drug, which is surface area, agitation, and temperature. So, how surface area is affected, yeah, or surface area can be affected. So, surface area, how can surface area affect the solvation? So, as we know, greater the surface area, more will be the solvation. So then agitation, as we know, if we try to shake or agitate the solute particles, they will be on they will achieve more kinetic energy as we agitate our solution, or our means our doses form in that of the solvent which is has been used. So by agitating, it will gain more kinetic energy, so that more kinetic energy and more solvation will be achieved. Then comes temperature. Again, temperature, rise of temperature can leads to have more kinetic energy. The particles or the solute molecules which will have more kinetic energy, and ultimately the solvation will be increased. Then comes association. So what is the association? It is the chemical reaction by ions or opposite electrical charge come together in a solution to form a distinct chemical entity. So means by chemical reaction, two oppositely charged ions or electrical charge atoms comes together in a close entity to in a close proximity, we can say, to form a different or distinct chemical entity. The focus involved in the attraction of opposite electric charge are electrostatic bonds. Then come ion associates, have been characterized by means of vibration spectroscopy. So we can characterize these ion associates with the means of the vibration spectroscopy. Then the most important factor to determine the extent of ion association is dielectric constant. So what is dielectric constant? Then question comes, what is dielectric constant and how dielectric constant can be measured or determined. So the dielectric constant is basically a polarity check or a polarity index that will be helpful to know whether our solute solvent mixture or our solution is polar or not polar. So it means what? Greater the polarity means greater the dielectric constant. So it is what? It is the ratio between the permittivity of the medium to the permittivity of the free space, or we can say vacuum. So it is the relative permittivity of the medium, that medium which we have to find which we have to find dielectric constant and to the permittivity of the free space. Then how will we determine the dielectric constant? How will we measure the dielectric constant? The dielectric constant of the solvent is measured by determining the conductance between the two plates. Then after that, the conductance by maintaining the vacuum between the two plates. Then we'll find out the ratio between the first conductance and second conductance, which will give us the dielectric constant. Then ultimately the factors which will affect the solubility of drugs. So there are various factors that can affect the solubility of drugs, which are temperature, molecular structure, particle size, and many more. But due to shortage of time, I've just got 3 of them. So I'll be explaining the effect of temperature on the solubility, or we can say solubility of drug. So most of these solids dissolve with absorption of heat, and the solubility of such solids increase as the temperature increase. So we can say there are many types of solids which maybe absorb the heat. if this is the case, then the solubility will be increased in that particular solid. And if we can say in some solid there will be the evolution of heat, and if there will be the evolution of heat, then then with the increase of heat, yeah, increase of temperature, we can say solubility will be decreased. Then that what's the case of NaCl. Then comes the molecular structure. So molecular structure can also affect the drug's solubility, as the slight modifications in the molecular structure can change the results of solubility, because if molecular structure will change, then properties will also change, and hence the solubility will also change. Then our last is particle size. Then particle size, how particle, then question comes, how particle size will affect the solubility. So as we know, as the greater the particle size, uh, larger the surface area. Then particle size, if smaller the particle size, then the surface area will be large. If we reduce the particle surface size, if we particularly try to reduce a size of a particular solid, then the surface area will be increased, and if surface area will increase, ultimately the solubility will also increase, as the solid particle will have more, we can say, more of the environment, or more of the uh, will have more of that, means surrounding, or we can say membrane, biological membrane, so that it can pass through that membrane or through that biological system. So the greater will be the greater will be the surface area, greater will be the solubility. So these are the factors that will these are some of the factors which affect the solubility of drugs. There are many other factors also, which are pH, and dielectric constant also is also there, and uh, other factors. uh, so uh, now, thank you. I'll end this presentation by this.